Hello, everyone, and welcome to our webinar number 5 on heat flow prediction with TemisFlow. We are very happy to be with you today, so thank you for registering and attending the meeting, and we hope you'll find it interesting and useful. Your main speaker today will be Alcide Thébault, and I will be the moderator of the event. My name is Marie-Caille. Both of us have been working with Basip for nearly 10 years. We've been working in the software development team, especially on basin modeling solutions, including TemisFlow. So we hope we'll be able to give you a good presentation and answer the questions you may have. Before we start the meetings, here are a few guidelines. So as you probably noticed, you are all automatically muted, so you cannot speak. If you have questions during the presentation, you can use the questions panel that is located at right-hand side, and we will have some Q&A breaks when we will be able to answer them. However, do not wait for those breaks to write your questions down, otherwise we might have a hard time to answer all of them. If we cannot address all your questions live, we will do it afterwards by email. On the right, you will also find a polls panel in which we will ask you questions from time to time. So if you can check it out, that would be great. And finally, the full meeting is recorded, so we will post it on our YouTube channel in a few days after today. And I will leave the stage to Alcide now. Thank you all.
Thank you, Marie, and hello, everyone. So this is the agenda of the presentation today. So I will start by telling you a bit about the theory and the concepts of thermal modeling in TemisFlow, and I will give you a review of the different approaches we have. We will follow that by a short Q&A break and then move to some examples of applications in passive margin settings and the presentation, the webinar, with a second Q&A break. So first, what are the concepts that we handle in TemisFlow for thermal modeling? So there are several phenomena that we need to consider. So first, we need to take into account several heat sources that are present within the sedimentary basin. So we have to take into account the surface temperature, which is a result of the atmosphere when we are onshore and the hydrosphere when we are offshore. We have to take into account the heat that comes from the mantle and the core. We have to take into account the radioactivity that is generated by a radioactive decay, which is very important in the upper crust and can be important in the sediments. And we can also take into account magmatic intrusions like volcanic sills and dikes. The other processes are usually considered to be marginal in basin models. Second, we have to take into account the transfer of the heat within the basin. So that transfer can be of two types. It can be done by conduction, which is the heat transferred through a solid, through the conductivity of a solid, which is always important. And it can be also heat transferred by convection, which is transferred by fluids, by the water, and which is important if there is hydrothermalism. So how do we integrate all that within the model in order to compute the thermal state through time? So we have to define several elements. So the first main elements that we have to consider are three main elements. The first one is the top condition, which is the surface temperature through time. The second one is the bottom condition, which is usually the heat flow at the base of the sediments that originates from the inner earth. And the third main elements are the thermal conductivities of the sediments. Other elements have to be integrated and taken into account, which represent a local disturbance like the salt, the volcanism, the impact of erosion, of hydrodynamism, and other impacts that may affect the thermal regime. So all that is actually related by a simple physical law, which is the Fourier's law, which tells us that the heat flow is the product of the thermal conductivity of the rocks, the elements, multiplied by the thermal gradient. Of course, there are other elements like the radioactivity, like the mass heat capacity for the lithologies that has to be taken into account. But here we will focus more on that aspect, which is the main one. And all that is integrated within a finite mesh computation with an O scheme where we take into account all the cells around one cell. So we take the thermal gradient in all directions and we solve the model as one through a matrix. I will not get into all those details. It's for you to realize that all that is integrated within a forward model. So let's actually have a look at all the main elements more in detail, and the first one is the impact of the thermal conductivity. So actually the thermal conductivity derives from the conductivity of the matrix of the rocks and the conductivity of the water, which is ponderated by the porosity. So here you see that we have an impact of the porosity of the rocks, which will evolve through time, evolve with depth, and an impact of the temperature, which also changes the conductivity. So that means the conductivity will vary with temperature and porosity and will of course have an impact on the thermal regime. So what we may not really be aware of is that the overpressure will have an impact on that thermal conductivity and on the thermicity of the basin. So for example, with an increase of overpressure, we have an increase of porosity, and with an increase of porosity, we tend to have an increase of the temperature within the basin. So this is what can be seen here in two sections that have the same thermal boundaries, so the same top and bottom boundaries. The one on the left is calibrated in pressure, the one on the right is just a simple hydrostatic model. And if we compare the results within the same cell, we see that of course the pressure is different, but what we may not be aware of is that the temperature will be different, with here a variation of 5% approximately. So here it's not a high impact, but it is an impact that can be important sometimes on the source rock maturity, and that shows us that you should always calibrate the model in pressure and in temperature at the same time, or sometimes even before in pressure. The second impact that I want to show you is the impact of salts that can be really well taken into account within a 2D or a 3D model. Actually, the salt has a very high conductivity, and which will bring a cooling effect below and on the side of the salts, and a heating effect above the salt. So actually here, if we look at the norm of the heat flow, we see that focus effect of the heat on top of the salt. And if we look at the isotherms, we see that the isotherms go up above the salt, which means that we should expect higher temperature at shallower depth. And underneath the salt, we have the opposite effect with lower temperature at the same depth level. So that will of course have an impact on the source rock maturity below and on the side and at the top of the salt bodies, which should be taken into account, and that will be a strong 2D or even 3D effect that has to be considered. Of course, that will also come from the restoration of the salt evolution through time, which will have an impact as well on the conductivity of the salt body. The other element that I want to discuss here is the magmatic intrusions. So these intrusions, like dikes for example, can have an impact on the source rock maturity because they have a very high temperature. So they arrive into the system with a high temperature, so usually around 1,000 degrees. But however, that impact will be quite local. So here, let's have a look at that example to see here. So we have classic sedimentary units with one intrusion that happens, that arrives within the model, which is a few hundred meters wide and a few meters thick. And this is the impact that we have in temperature. So before, we have a very consistent, homogeneous temperature regime. And once the intrusion occurred, we had that halo of temperature with a high temperature here where the intrusion occurs, and which will impact, so with a kind of metamorphic area around that intrusion. So through time, actually, if we take into account 3 cells located within the intrusion and on the side of the intrusion, we see that that impact is very local. So only it occurs in less than 0.1 million year, but the impact in terms of temperature can be relatively high. So here a few hundred degrees at geological scale, of course. So that will have an impact on the transformation ratio, where we see that around the dike, the transformation ratio of the source rock goes from 0 to 100 almost instantaneously. So we see that overall, a small dike will not have a very strong influence. The influence will be very local, but if we have a large size intrusion, it may supply heat to a larger extent and may have a regional influence that should be taken into account. Here we have some elements that can be taken into account, but what we should also take into account is that the thermal regime is never really steady, and that we will have some elements that will make it transient, that will make it vary, and will have longer scale impacts. So for example, a fast sedimentation in a relatively short amount of time will tend to destabilize the steady state. So if we start from a constant thermal gradient, if we have an instantaneous deposition at geological ages, once again, at a surface temperature, what we see is that we have that decrease, a global cooling of the upper column that we call a blanketing effect, and that will tend to destabilize here the thermal gradient. Same thing if we have an erosion. In that case, what happens is that we remove almost instantaneously the upper section, some material, and that will tend to heat the upper column, and that we will tend to have higher thermal gradients and higher temperatures at shallower depths. So that should be taken into account. And actually what people may not be aware of is that this impact, which occurs within the sedimentary column, will have an impact all the way down to the crust. So here, if we actually couple at the same time the sedimentary model and the crustal model, so here described with the upper crust, lower crust, and mantle, we see that the heat flow disturbance occurs all the way down to the crust. So these effects are transient, evolve spatially and through time, and involve both the sedimentary model and the crust. So how do we integrate that precisely, and what are the different approaches that can be taken into account? So as I said, two conditions have to be taken into account in the model. So a surface condition and a bottom condition. So as for the surface condition, it's driven by the surface temperatures, which depend on, first of all, the elevation, the bathymetry, the depth at the top of the sediment. So here is an example offshore where the surface temperature can be linked to the bathymetry. So through a relatively simple law, which is an exponential decay of the temperature with water depth. And that surface temperature through time will also depend on the location of the basin through time. So its latitude variation and potentially the impact of paleocurrents. So the latitude variation can be taken from bibliography. So here, for example, from Scotty's information here, which comes from paleo reconstructions. And through that paleo reconstruction, we will be able to know what is the surface temperature evolution through time. So all that can be actually automatically computed through a new functionality that has been implemented in the 2020 version of TemisFlow. The second condition that we need to define is the basal thermal boundary. So the first way of defining that is usually through a simplistic approach, either with a thermal gradient, which is just we relate the depth of the sediments to a certain temperature. There is no impact of the conductivity, no impact of the heat. So it's very basic, very simple, and very quick. And the other simple approach is to use a base sediment heat flow. So usually to have that information, what we do is we calibrate the model at well location with a 1D approach. We calibrate, we find the right heat flow at the base of the sediments, which will explain the temperature at well location, and we extrapolate that laterally. So that tends to bring what we call a smallpox mapping, which has nothing to see with geology. So usually that approach is to avoid because it doesn't even bring good heat flow correlation at present day, especially when you are far away from wells, and that evolution through time is even worse. So here what we recommend, and the solution that we usually use in TemisFlow, is to use as a basal thermal boundary a lithospheric model that is fully coupled with the sedimentary model. So that lithospheric model represents the crust, upper crust, lower crust, and the lithospheric mantle. And its base is usually a deep layer that is said to be the lithosphere-asthenosphere boundary. And we usually associate that lithosphere-asthenosphere boundary to the isotherm 1300 or 1333 degrees Celsius. So this lithospheric model will reproduce all the main lithospheric processes, including rifting events. And the idea is by coupling that model, we can bring a geological understanding and of the heat flow at the base of sediments, which becomes physically consistent laterally and through time. So what are the different options that we can have for that lithosphere model? So all that will be derived from a beta factor concept, which is the relationship, the ratio between the initial thickness of each unit of the model compared to its thickness after the rifting events. So all that is derived from the Mackenzie model, which goes all the way back to 1978, where the lithospheric model is described by upper crust, lower crust, and the lithospheric mantle. And we define one beta factor, which is homogeneous, and which will drive the thinning of each unit. So here, actually, what we see is that the total thickness remains the same, and actually the base of the models is actually just an isotherm that rises from a certain depth to another. So I will show you that afterwards in an example, but here the total thickness doesn't change, only the thickness of the crust, and the thermal heat is brought through the rise of the isotherm. Then the relaxation is done automatically by bringing back that isotherm to its initial depth once the rifting event is over. The second methodology is the basic option actually in TemisFlow, which we call the improved Mackenzie model. In that case, we also have 3 units, but the beta factor is defined as heterogeneous. So we can have a different beta factor for the upper crust, the lower crust, and for the thermal beta factor. So the thermal beta factor can be decoupled from the geometric crustal beta factor. So that's the second one, and in that case as well, the decrease will be automatic. The third model, which we call the flexible model, actually doesn't have only 3 units. It can have as many units as you want, so you can split the crust and the mantle however you want. In terms of beta factor, it's the same. The beta factor is heterogeneous, but what you can do is that the lithosphere, the base of the lithosphere can be manually adjusted. So you can actually have a geometric beta factor for the upper mantle. So you can bring physically the base of the mantle up, maintain it high if you want through time, and you are the one who controls the relaxation phase afterwards. And you can also have some beta factors that are infinite, which means that you can have some layers that will appear in order to model some effects like serpentinization, for example. So why is it important to take that into account? So here let's have a look at a model offshore Canada, which shows intense rifting and magmatism. So this is the description of the crust at present day. So here we have some continental crust that goes to oceanic crust with thickness. So here is the moho depth here, so the total thickness of the crust with a relatively thickness close to the shore and something that is hyperextended more distally. So that comes from present day interpretation. And what we actually see is that the first deep offshore wells were drilled after the study. So within the hyperextended crust domain, and they are more than 50 kilometers away from the closest calibration, which is on the shelf, which was used at the time of the modeling to calibrate the model. So in an area that was far from any observed data and that was not directly calibrated, only calibrated through that lithosphere model coupled to the sedimentary model, we see that we have a perfect match between the observed data and the predicted data at well location, so both in terms of vitrinite and temperature and pressure at present day. So this is why it is important, is that because you can trust your model even in areas that are far from your calibration points. So this concludes the theoretical aspect of the presentation. So Marie, I don't know if we have any questions.
Yes, we have one question. Will the cell size have an impact on the lateral and vertical impact of the intrusion? When you show the intrusion slide.
Yes, well, actually, the physical impact will not be that different, but I mean, of course, the resolution where the dike is will be important because that will define the thickness and the extension of the body. So the thicker or the wider it is, the more impact it will have. But around the dike, actually, the physical computation will be similar, except you will have maybe less description of the conductivity, but the physical phenomena will be the same. The main difference will be with the representation of the property. So if you have a higher resolution, you will be able to see the variation of your temperature laterally or vertically. So here, yes, it's of course always better to have a higher resolution, but in terms of physics behind it, the physics will always be the same.
Thank you, Sid. We have another question. Does the flexible model take into account the stretching of sediments?
So yes, it will take into account the stretching of sediments by changing the thickness through time. So you can have it vary, and you can even actually have it down to zero. So you can have an hyperextended margin where the crust totally disappears. The only thing is it will be only vertical variations. So you won't model the extension of the basin, but which is also the case with a regular heat flow, and it's actually more linked to the vertical pillar grid that we have rather than with the model in itself for the crust.
What about anisotropy of thermal conductivity? Is it accounted for?
Yes. Yes, that is a good point. So it's true that I only showed you here the main elements. I didn't get into detail with every single thing that we can take into account, but it's true that I should have mentioned it. You can actually take an anisotropy into account, so either vertical or horizontal in the two directions. So you have actually, depending on how you define your model, you have an X and a Y direction. So you can define a difference in anisotropy in these two directions. And you can also have a vertical anisotropy. And actually that will be taken into account through the conductivity. So the conductivity of the sediments will vary depending on the direction of the heat.
Next question, how do we compute heat flow in the case of multiple rift settings?
So
in other words, can we account for multiple rift?
So yes, so how it would be exactly the same thing, except that your rift will be in several phases. So here, of course, to simplify things, I only presented you one phase with one thinning of the crust, but actually you can have as many phases as you want through time with a different beta factor every single time. So you can actually imagine to have a positive a beta factor above one, which will correspond to a thinning, but you can also, through time, have a beta factor below one, which will correspond to a thickening of your crust if for some reason you have some thickening that may occur through time. So everything is possible, and you can have that polyphased rifting defined without any problem.
Last question is related to hydrothermalism. Is the hydrothermal resources, can the hydrothermal resources affect the heat transfer?
So yes, so this is more linked to the convection. You can also take into account the hydrothermalism. So you need to actually, it's an option that you need to activate because it will make the process a little bit slower, but that can be taken into account. In that case, the heat will be transferred with the water. So actually the way it works is that the water is cool first, it goes into deeper depth and it may get heated, and then that heat is transferred with the water a bit further out in your aquifer, and that will heat the system in that area. So yes, in that case, the water acts as a source of heat, and that can be considered with the migration of the water within the system.
I think this is it. Yes. I see you can move ahead with the case studies.
Okay. Thank you. So here are two examples of applications in passive margin settings. So the first one will be in the Brazilian margin. So that margin is actually characterized mostly by that thick salt layer and by its evolution that is directly linked to the opening of the South Atlantic Ocean. So this salt thickness separates the system into two systems, one which is pre-salt and the other one which is post-salt. And the pre-salt system is, as I said, occurring actually during the opening of the rifting. Here, to properly characterize that rifting event, we start from, so we use, of course, a lithosphere model that would be coupled to the sedimentary model. And its initial state is as shown here, so with a continental crust which has a continuous thickness laterally. And through time, so until present day, we have first a thinning of the crust which varies laterally. So here we pretty much keep the continental thickness here, when here we move to an oceanic crust. So this is done through beta factors which vary laterally. And on top of that, we also change the lithology through time. So in order to simulate the intrusion of basic rocks in the crust, in order to represent here some mantle exhumation, and here to represent the modification of oceanic crust, so from continental crust to oceanic crust. So this is the physical representation of the phenomena through time. So here we have the rifting phase with a thinning of the crust. So at the end of the rifting phase, we have first an exhumation, which is here represented by a lithology change, so to represent that the mantle goes up. And then at the moment of the beginning of the relaxation phase, we have here the arrival of a crust which will have less radioactivity, of course, and a different thermal behavior. And then we have the burial of the basin with the deposition of the sediments. So how does that translate in terms of temperature? So here what you saw is that the total thickness remains the same, but actually with the rifting events, we have a rise of the thermal isotherm. So here the 1300 degrees isotherm that goes up here through the rifting process. So it goes all the way up to 125 million years. And then we have a relaxation phase that cools down the basin. And so this is done by, at 125 million years, putting back the isotherm at the bottom of the model. And then it's just the dispersion of heat that will cool down little by little, so in a few tens of millions of years, the basin. So how does that translate in terms of heat brought to the sediments? So this is the representation of the heat at present day. So you can see that it's an effect of the heat coming from the crust, but it is also an effect of some sedimentary processes. So for example, right here we have the effect of the salt that can be really seen here, so that I mentioned before, with a strong heat on top of the salt and a lower heat below the salt. And here we have the effect of the high sedimentation rates that tends to cool down the basin, which is what we call the blanketing effect. So here we can have a look as well at the evolution of the heat through time. So what we will observe is that we have first an increase of the heat during the rifting phase, but that effect is different along the basin, with a much important impact in the distal area. And then through the relaxation phase, we can see that in some areas that relaxation phase will be even stronger, amplified by the deposition of the sediments. So that history will actually have an impact on the source rock maturity and the timing of the expulsion of the sediments. So here, what we observe at present day, so for the three main source rocks, is that most of the source rocks, especially the deepest ones, are within the gas window, but this source rock right here is within the gas window in some areas and within the oil window in some areas. And we see that these oil windows are related to the presence of the salt, which will tend to cool the basin and have an impact on the maturity. So here we can expect actually a bit less hydrocarbon and more oil-prone source rock rather than gas-prone source rock. So that is actually important as well, because that expulsion will be also timed with the opening of the salt. So the salt windows that will allow or not migration. So depending on when the migration occurs, we may or may not have a transfer of the hydrocarbons to the upper system. So the second example that I wanted to show you is on the other side of the Atlantic Ocean. So it's on the Iberia margin, offshore Portugal. So here it's an hyper-extended system where we see that the crust actually totally disappears in some areas, and where we have a very nice reconstruction of the lithosphere through time through a paper done by Sutra et al. So this is the evolution of the lithosphere that was done, which is a polyphase rifting. So I won't get into too much detail, but you have a first phase of stretching followed by a second phase of hyperextension, in which what is interesting here is to see that we have a decoupling of the asthenosphere and the crustal thinning. So we see that we first have the asthenosphere rise, and then we have the crustal thinning. So we see here that we need to have some beta factors that are decoupled between the asthenosphere and the crust to properly represent the history of the crust through time. So this is the model that was done within TemisFlow, so both in terms of stratigraphy and lithology. So we see here that we have 3 units within the crust and 2 units within the upper mantle, and that we have defined a certain conductivity and productivity and radiogenic productivity for each lithology defined within the system. So here there is no oceanic crust, but it's an hyper-extended continental crust. So this is the reconstruction, and here we used the new module, the new model, which allows us to bring up the asthenosphere and control the uplift of that asthenosphere, and control when we have the decrease, and decouple very nicely and perfectly the uplift of the asthenosphere from the thinning of the crust. So here the relaxation phase is then done manually, so it's up to the user to define when it occurs. So you can compute that through an exponential decay law, and you can take that into account. Here what you see as well is that in some areas, if I go back, the crust totally disappears, and we have some thicknesses where the crust becomes equal to 0. So what is the impact in terms of thermal regime? So this is the thermal evolution through time with that uplift of the isotherm that is physically represented. And how does that translate in terms of heat? So here we see that with the rifting event, we have a strong heat flow that is here occurs in the distal part, with actually where the asthenosphere becomes close to the surface, stronger even heat flow. And here we have less heat brought within the continental part. And then during the relaxation phase, everything becomes more homogeneous. And we see that the small impacts of heat are brought by the areas where we have either a where we have a low sedimentation and a strong presence of the continental crust. So this is what we see here, actually at present day, where we can relate the presence of heat to either a strong presence of the continental crust, or actually lower heat where we have a high sedimentation rate. So here, once again, it's a coupling of the lithosphere effect and the crust, because we see here the general trend still comes from the crust, and the local trend comes from the mini basins that are present within the sedimentary model. So the model was calibrated in terms of heat flow measurements. So we used heat flow measurements at the surface that came from drilling campaigns, and we see that the model is very nicely calibrated at different locations within the model. So that translates, so that is the calibration at present day, but through time, the evolution is actually very similar to what we've seen in the Brazilian case, with a stronger heat that is brought during the rifting event in the distal area. Then here, the difference is that we have the effect of the mantle sedimentization that will actually keep the heat a little bit, and the fact also that we maintain the asthenosphere up. So we have actually stronger heat that stays longer through time, with a limited effect on the shelf here for the rifts, and then everything cools down with a blanketing effect due to the deposition of the sediments. So this translates in terms of maturity to what we observe here in terms of vitrinite reflectance, with a very high vitrinite reflectance in the distal offshore part, and a lower vitrinite reflectance here in the continental part, even though the sediment thickness is higher. So actually, this is the result of one model, but that model has very little calibration points, and there can be some variability, and there is a lot of unknown in terms of all the parameters that we've used for the lithosphere model. So here we perform an uncertainty analysis in order to understand what is the variability and the risk associated to that model. So we take into account three main uncertain parameters, which will be the conductivities of the lithosphere facies, the radiogenic production of those lithologies, and the asthenosphere depth limit. We define a range of variation, so either in terms of values or in terms of depth here, so the minimum depth or the maximum depth that we should expect for the asthenosphere rise. And we launch 12 simulations. Here, first, we make sure that all the simulations are as well calibrated and can all be accepted and that they are equiprobable. And we see that in every single case, the present day heat flow actually matches the measurements with an 88% overall calibration that is observed for each simulation and that results from actually different levels of calibration at every well location, but the overall calibration is very similar. So once we have done that, we can use a response surface-based approach in order to perform a sensitivity analysis. So we interpolate the behavior of the calculator here to approximate the vitrinite reflectance value, and we launch a Monte Carlo on that response surface. So we mimic 100,000 simulations from only 12 simulations. So here, this is the result of the sensitivity analysis. So we see that, relatively speaking, the asthenosphere limit is by far the most impacting parameters compared to the conductivity and the radiogenic production. And that drives actually a different history in terms of evolution of the vitrinite reflectance. So this is the vitrinite reflectance through time. So in blue, the P50, in pink, the P90 and P10, and in dashed lines, the P0, P100. So that means here is the total range of possibilities that we have. So at present day, we see that we have a vitrinite reflectance range that goes from 1% at a minimum, which is within the oil window, to 1.6 for the best case scenario, which is in that case within the gas window. And that translates into a risk for the entry age in the oil window, which is not very risky, around 129 million years in every case. So here we can time the entry in the oil window pretty precisely, but the entry age within the gas window can occur as soon as 120 million years or cannot occur at all. So that is also very interesting because we can see here the fact that we de-risk the presence of oil, but we can have a risk on the quality of the oil, whether it is gas prone or not. So in conclusion, I want to insist on the fact that nothing is constant, neither laterally, vertically, nor through time. So if we actually look at the temperature evolution laterally or the thermal gradient evolution vertically, we see that it cannot be approximated by something that is constant. Here you see that the thermal gradient varies vertically, varies laterally. Same thing with the heat flow at the base of the sediments. You see that there is no easy interpolation that can be done, and it comes from a coupling of all the phenomena, and that's only that way that you will be able to take everything into account. So our recommendation will be to always use a model with sediments and lithosphere fully coupled, in which you define a deep base for the model within the lithosphere that will act as a buffer. And you should not be shy in building that lithospheric model, because actually it's not as hard as it seems, because it's actually quite easy to find or compute the Moho depth. So there are a lot of bibliography that give you an overall approximation of what is the Moho depth at present day throughout the world. You have a lot of bibliography and analogs in order to distribute your crustal lithologies. You can easily check as well the presence of hotspots, mantle plumes, magmatism, and so on into your model. And actually, you should always start simple and add complexity afterwards if needed, and if you see that it will have an impact on your thermal regime. So in the end, with a few calibration points, coupling a simple lithospheric model with a basin model will always give better results. So this concludes the presentation, and we can move to the last Q&A break.
Yes, I see we have a few questions. The first one goes back to the mesh resolution. What is the rule of thumb to define the vertical and horizontal cell size during modeling?
Oof. It depends on a lot of things. It will depend on your objectives. It will depend on the data, the quality of the data you have. It will depend on the time that you have. Usually the lateral resolution is kilometric or hundreds, from 100 meters to kilometric size. But then if you want to as we were talking before, if you want to check the impact of an intrusion, maybe you want a thinner more precise resolution, and the vertical resolution will actually depend on your seismic interpretation and on the resolution that you can bring in your facies description. And in that case, it will be metric in some areas, or it can be 100 of meters where you have a high sedimentation rate, or where you do not have that much information.
And it also depends on the level of details that you want to get in your final results.
Yes.
Can you suggest the thermal properties of upper mantle, lower crust, and upper crust during the thermal modeling? Do we have default parameters?
So yes, exactly. So it's true that I didn't mention that, but in Temis, that geometric behavior is coupled or is associated to what we call a lithology library, and in that library you have all the petrophysical behaviors of your different facies, and these facies will have their own radiogenic production, thermal conductivity, mass heat capacity, and so on. And you have some default parameters, default lithologies that you can use as reference, and you can of course tune them, modify them, either because you have some bibliography information or some lab measurements, or through your calibration process you can also adapt these default values.
What do you think about the practice of thermal modeling by implementing the heat flow maps at the border basement sediment cover, ignoring the crust? If this approach is correct, then in what type of basin this could be applied?
So if we follow the conclusion of that presentation, I would say that for me using the heat flow map will always be an approximation. So I would say the only case where it's relevant is where you have almost no crustal impact and where the crust doesn't really vary through time. So either in very old basins where you don't really care about what happened deep in the basin, but for sure in passive margin settings, that approach would not work. Other areas where it could be okay is where you have a lot of calibration points. So if you have lots and lots of wells in an area, you could approximate the fact that you are able to properly calibrate your model with your well data and then extrapolate the information. But even in that case, it would still be better to calibrate at well location using a crustal model and interpolating through your crustal properties. So personally, I would say that either because you don't have the time or because you don't have the knowledge to do it, you should use a heat flow at the base of the sediments, which can be an okay approximation. But if you want to have a physically sound approach, you should always couple with a lithosphere model.
Does the user have possibility to set his own mixing rule for bulk thermal conductivity?
So yes, actually you can create new lithologies by mixing existing ones, and in that case you can use whatever method you want. So either an homogeneous mix or an arithmetic mix, or with the computation of an average. Or you could also compute it totally independently in an Excel spreadsheet, for example, and bring in the final result that you want within the system.
All right, and then we have two questions on the Iberian example. First one is, have you tried out a thick layer of basalt at the base of sediments, and does the high heat flow still persist in this case? So I will answer that one saying that no, we haven't tried that. If we were to try this, for sure we should see an impact on the heat flow calculation in the model. Second question on Iberia. So we used heat flow measurements from ODP, DSDP campaign. We also use some present-day temperature data sets. So in that case, the answer is no, because there were no such data available. We only had a few vitrinite measurements on a well located 40, 50 kilometers north of the section. No temperature measurements. We have other questions. Can we see these explanations in practice, for example, in the help? I think so. If you check out the documentation of Temis, you will see some theory booklets on all the basement model implemented in the software. So they might not be illustrations, but you will have some background on the equations that are used and the phenomena that are accounted for. Okay, so we have another question still related to the invariant case. So surface heat flows tend to be more in deeper waters, while the sediments don't really show high VR0 measurements when drilled. It is an observation, and our comments on that would be appreciated.
Well, yes, indeed, the heat flow measurement is well, it's just a representation of what we have at the surface. What is at present day, it is of course impacted as well by the water, the ocean that is here. In that case, so this is just a representation, but and of what we have at present day, and doesn't reflect at all what you would have through time. So as Marie mentioned, we had one well that I didn't mention here because it's actually a bit far, but which allowed us to validate the trends. But actually here in that case, more than validating the model through observed data, it was more validated through the approach that was used. So because we know that this lithosphere approach that we use was validated in other areas like the Canadian margin, Brazilian margin, West Africa margin, and also in a lot of other areas, we know that this approach is valid and has been validated in other areas. So here was to show that even if you have very little data, and in that case just heat flow, which is not at all, as you said, a representation of what occurred through time and which is recorded within the vitrinite reflectance, we can still have an information, and an information that is relevant and that can be used for exploration purposes. And you can actually check what is the risk of your analysis, and you don't have just one result, you have actually a range of results in order to have your best case and worst case scenarios through that sensitivity analysis approach.
Yes, absolutely. It's a bit tricky, and the past history can have different indications from the present day model. One last question to finish. How exactly thermal and structural solutions are coupled? Does your algorithm include some relaxation parameters?
So, well, everything is coupled in the sense that when we perform the simulation, if you have a sedimentary model and a crust model, for the calculator, they are just considered as one, and the interface between the crust and the sediment is just the same as the interface between two layers within your sedimentary model. So actually for the calculator, it's just one unique model with the sediment and the crust. So then, as I mentioned quickly, we use a finite element approach with an O scheme where we write through equations every single thermal relationship that you may have, and we solve that equation as a matrix through a solver. So we have different solvers. So all that is taken into account with the boundary limits, and we have a result from that, which is the heat flow throughout the model and the temperature throughout the model. In terms of relaxation, actually what is done is that we control, it will depend on the model. So if I take the basic Mackenzie, we control the rise of the asthenosphere. And then for the relaxation phase, actually what is done is we just bring instantaneously the isotherm at the base of the model. But because we have a mass heat capacity, because the sediments will keep, not the sediments in that case, but because the crust will keep the heat, it will take time to actually cool down, and that will be automatically modeled through the mass heat capacity of the facies, and that will be automatically integrated and taken into account. For the other model, where we actually modify the geometry, so for the advanced model, in that case, the relaxation phase has to be done manually. So you have to estimate what it would be. So for that, you can use an exponential decay law, you can use the basic approach, and you can yourself bring the temperature down. So I hope that was clear. It's true that it's quite advanced, but that's the that's the answer I can give you.
All right, I think that is it for now. Thank you very much, everyone. We hope we passed the message that we really believe in that thermal coupling between the lithosphere and the sediment, and that this should be the approach used in most of the cases. We can start simple and add complexity if needed, so we should not be afraid of running such models. Thank you very much for the very interactive session. We had a lot of questions. Feel free to contact us afterwards if you need more information on TemisFlow. We'll be happy to provide trial licenses if needed. And yes, this is it. So have a great day. Thank you very much, and we look forward to seeing you again in our future webinars. And just before we close the meeting, please have a look at the polls tab where we have 2 questions for you. Thank you.